Every law of physics we have ever written describes how things change. Not one of them describes how something stops existing. Not one. And when you sit with that long enough, the word death starts to mean something completely different than what you thought. Tonight, we are going to walk through what relativity, quantum mechanics, thermodynamics, and deep time cosmology actually say happens when a life ends. And the answer is genuinely stranger than anything religion or biology prepared you for. If you are new here, welcome to Sundown Science. Hit subscribe, pour something warm, and get comfortable. Because what we are about to work through tonight will quietly change how you think about your own existence. Now, settle in and let's ease into this one slowly. Part 1. The false ending physics never actually describes. Something ends when you die. That much feels obvious. The body stops, the brain goes quiet, and whatever was animating the whole project of being you, the accumulating memories, the preferences, the particular way you laugh, ceases to operate. We call this death, and we treat it as perhaps the single most fundamental event in human experience, the ending, the full stop, the switch flipped to off. Except physics never describes that. Not once. Not in any equation, in any framework, in any corner of the physical sciences going back to Newton. And that absence, quiet, technical, easy to miss, turns out to be one of the strangest facts in all of science. Think about what physics actually does. It describes how things evolve. It tracks the way a system in one state transitions into another state over time. Newtonian mechanics gives you trajectories, the smooth path of a ball from here to there. General relativity gives you the geometry of spacetime, the fabric of reality itself, bent and curved by mass and energy. Quantum mechanics gives you the wave function, a mathematical object encoding every possible way a physical system can behave, evolving forward in time according to precise, unbroken rules. Thermodynamics gives you entropy, the tendency of complex ordered structures to drift toward disorder over time. All of these are frameworks for tracking transformation. None of them contain a term, no variable, no operator, no function that corresponds to the thing we casually call death, the total erasure of a person from existence. That is not a philosophical statement, it is a technical one. You can write out the equations governing every known force and field in the universe and search every symbol for something that performs ontological deletion, the act of removing something that existed from the inventory of things that exist, and you will find nothing. The math just does not have that operation. The universe, as best physics can describe it, is a system that transforms. It is not a system that erases. Classical mechanics operates entirely within the framework of phase space, an abstract mathematical space where every possible state of a physical system corresponds to a single point, and the evolution of that system is a path through that space. The second law of thermodynamics aside, the equations governing classical systems are time-symmetric. They describe change, movement, transition from one configuration to another. They do not describe any point on that path vanishing. Phase space volume is conserved. States become other states. Nothing disappears. Relativity makes this even more geometrically explicit, and we will get into the full strangeness of that in the next act. But for now, just hold this. In the relativistic description of reality, space-time is a four-dimensional structure in which every event, every moment, at every location is a coordinate. Not a fleeting instant that exists and then disappears. A coordinate, embedded in the geometry of the universe. The moment you are reading this or hearing this is not happening and then ceasing to happen. It is a point in a structure. Quantum theory is even more insistent on this point. The Schrödinger equation, which governs how quantum systems evolve, is unitary. That is a technical word meaning information preserving. A quantum system evolving forward in time does not lose anything. The total information encoded in the wave function is conserved. Even apparent collapses, apparent endings, are, depending on interpretation, either branching of the wave function or redistribution of correlations. The system changes, it does not delete. And thermodynamics, the one discipline that most loudly announces the direction of time, the one that gives us the concept of irreversible change, even here, the microscopic states that composed a system never cease to exist. Entropy increases, structure dissolves, but the atoms that formed that structure remain. The energy that organized them persists, spreading outward, distributing itself through the environment. The order decreases. The existence does not. So here is the question that will run underneath every single thing we discuss from this point forward. The folk model of death, the intuitive idea that you exist and then you stop existing, and there is a clear dividing line between those two states, does not appear anywhere in the fundamental laws of physics. The biology of death is real. The experience of loss is real. But the physics version of what we think death is, full cessation, deletion, removal, is nowhere to be found in the equations, which means something else is happening. Something the equations are describing that we are not looking at directly. And to find it, we have to start by asking what law of physics would even perform that deletion if it existed. Part 2. The missing operation in the laws of physics. Ask yourself a direct question. What physical process turns something that exists into something that does not exist? Not something that changes, not something that disperses, not something that becomes unrecognizable. What process, following from any known law of physics, removes something from the inventory of reality altogether? Try to name one. You will find that you cannot, not because the question is vague, but because the operation itself does not exist in the physics toolkit. Conservation of energy is the starting point. Energy cannot be created or destroyed. It transforms between forms, between kinetic and potential, and thermal and electromagnetic, but the total remains constant. This is not an approximation or a useful simplification. It is a fundamental symmetry of nature, derived from the time translation symmetry of physical law by Noether's theorem. The energy that constitutes you, the chemical energy in your molecules, the electrical energy in your neural signals, the thermal energy of your body, none of it disappears when you die. It redistributes. It does work in the environment. It becomes heat, becomes chemical energy in the organisms that decompose you, becomes motion in the air and soil, but it is all there, every joule conserved. Quantum field theory extends this further. In the standard model of particle physics, the fundamental reality is not particles, but fields, continuous structures pervading all of space. What we call particles are excitations of those fields, ripples in the underlying substrate. When a particle is destroyed in a high-energy collision, what actually happens is that its field excitation transforms, redistributing energy and momentum into other excitations, other ripples in other fields. The total field configuration evolves. Nothing is removed from the fields themselves. The universe is not a ledger from which entries can be deleted. It is a dynamic system whose entries are always transforming. General relativity treats spacetime itself as a geometric structure, and the events within it, every collision, every decay, every configuration of matter at every moment, are features of that geometry. You cannot delete a feature of a geometry without rewriting the geometry itself. And physics does not describe any mechanism by which the geometry of spacetime is being continuously rewritten to erase past events. Those events are embedded. They remain as coordinates in a manifold, in a sense we will explore in detail when we get to the block universe. Here is a useful analogy. Think of physics as a very sophisticated programming language. It has operations, addition, multiplication, transformation, rotation, evolution, forward in time. It has rules about what those operations do to physical states. But there is no delete function. no remove from existence operator, no command that takes a configuration of matter and energy and simply zero writes it out of the system. If you wrote a physics simulation of the entire universe, you would have functions for every known interaction: gravity, electromagnetism, the strong and weak nuclear forces, and none of them would look like erasure. They would all look like transformation. Now, the information picture adds another layer to this. Information, in the technical, physical sense, the number of distinguishable states a system can occupy, is something that physics treats with extraordinary care. The question of whether physical processes can destroy information is not a philosophical question in modern physics. It is a technical one with experimental consequences. And the mainstream answer, the one supported by quantum mechanics and most seriously defended by leading theoretical physicists, is that information cannot be destroyed. It can be scrambled beyond any practical possibility of recovery. It can be distributed across an enormous number of degrees of freedom, but it is preserved in the total state of the system. We will get to the black hole information paradox in a later act, and that is where this idea was tested to its absolute limit and survived. So, when you die, what does physics describe? It describes matter and energy reorganizing. It describes complex ordered structures dissolving into simpler disordered states. It describes information becoming inaccessible, distributed across so many environmental degrees of freedom that no conceivable measurement could reassemble it. It describes a biological system ceasing to maintain itself against entropy. None of that is deletion. None of that is removal. All of it is transformation. And yet we experience death, our own mortality, the death of people we love, as absolute ending, as removal, as the production of a specific, terrible kind of nothing. So where does that experience of absolute ending come from, if the physics never actually produces one? That question leads us somewhere uncomfortable. It leads us to look at the observer, at you, and ask whether the sense of ending might be something that minds produce rather than something physics actually performs. Part 3. The observer illusion of ending. There is a distinction that physics makes, quietly and consistently, that most of us spend our entire lives ignoring: the distinction between how the universe evolves and how the universe is experienced. Physics models the external description, the view from outside a system, tracking how its states change over time. It does not model first-person phenomenology. It does not have variables for what it is like to be inside the system. And this distinction matters enormously when we talk about death, because the thing that feels most terrifying about death, the thing that keeps people awake at 3 a.m, the thing that makes it feel like a genuine ending and not just a transformation, is the first-person version. The idea that your experience stops, that the inside view goes dark, that the continuous thread of consciousness, which has been present for every waking moment of your life, simply terminates. But here is the thing. Physics has no variable for that. Nowhere in any equation governing the behavior of matter and energy is there a marker that says, experience stops here. The brain is a physical system, and physics tracks the evolution of physical systems. As the brain ceases to function, its physical states evolve. Neurons stop firing in their normal coordinated patterns. Electrochemical gradients collapse. Temperature equilibrates with the environment. All of this is physical state evolution, and physics describes it. But the point at which the internal experience of that system, if it had one, transitions from something to nothing, no equation marks that moment. No physical threshold is crossed that distinguishes experiencing system from non-experiencing system in a way that physics can directly represent. This is related to one of the hardest unsolved problems in all of science, the hard problem of consciousness. Why does physical information processing give rise to subjective experience at all? Why is there something it is like to be you, rather than all of that neural computation happening in the dark, without any inner theatre? We genuinely do not know. And because we do not know how experience arises from physics, we cannot describe in physical terms when it ends. The neuroscience of dying tells us that neural coherence breaks down, that the last detectable signs of coordinated brain activity fade over minutes to hours after clinical death, that the process is gradual rather than instantaneous. But that is a description of the outside view, of what a third-person observer with equipment could measure. It is not a description of what happens to the inside view, because physics does not have access to inside views. What we call the moment of death, the subjective experience of existence ending, may not even be a coherent concept within physics. It is an interpretation layer. It is a narrative boundary that conscious beings impose on continuous physical processes, because we need categories, because we need beginnings and endings, because the human mind is a story-generating machine and it cannot help imposing narrative structure on reality. We say, she died at 2:47 in the morning, and that feels like a precise event, a moment when something happened. But what actually happened at 2:47 was that a biological system crossed an operational threshold, a point beyond which its integration and self-maintenance could not recover. The physics on either side of that moment is continuous. The state evolution did not pause. The universe did not mark the event with a special symbol, and this creates the central tension that will haunt the rest of this discussion. Physics consistently describes continuity. Experience consistently reports ending. These two accounts are not reconciled. They are not easily reconciled. The physics picture says, the universe transformed as it always does. The experiential picture says, something stopped. And the question of which picture is getting something wrong, whether physics is missing something crucial about the nature of mind, or whether our experience of endings is a kind of useful fiction, is one of the genuinely unresolved questions at the frontier of science and philosophy. But notice what we have established so far. Physics does not produce deletion. Physics does not mark the end of experience. And the intuitive folk model of death, the one we all carry around, the one that makes mortality terrifying in the specific way it is terrifying, does not correspond to anything in the fundamental equations. Whatever death is, it is not what we implicitly think it is. Part 4. The hidden consequence nobody notices. Pull all of this together and something comes into focus that is easy to miss when you look at any single piece of the argument. If the universe genuinely has no deletion mechanism, if every law of physics, from Newton's equations to quantum field theory to general relativity, is a law of transformation rather than erasure, then the ending you imagine when you imagine your own death is not what physics is describing, not because you survive in some comfortable or comforting sense, not because anything waits on the other side, but because the framing itself, the frame of cessation, of removal, of going from existing to not existing, does not correspond to a physical operation the universe can perform. What does physics describe instead? It describes death as a redistribution, a reconfiguration, a high complexity, locally ordered system, the thing that was you, transitioning into a lower complexity, more distributed state. Your matter scatters, your energy disperses, your information spreads outward into the environment, encoded in correlations so diffuse that no conceivable technology could read them back. You become, in the physics description, not nothing. You become differently arranged. This is what makes the topic simultaneously astonishing and unsettling, because it does not offer comfort in the religious sense. It does not promise continuation of experience, reunion, afterlife, or any of the narratives that human cultures have constructed to cope with mortality. What it offers is something stranger and, in a certain light, more radical, the suggestion that the universe's bookkeeping system never registered your deletion, because it has no category for deletion, only for change. And to understand why that is not just philosophical wordplay, to understand the hard physical evidence behind it, we need to move through 4 distinct pillars. The The first is geometry, specifically the geometry of spacetime, as described by relativity, and what it actually means for your life to be a permanent structure in a four-dimensional manifold. The second is information, and the extraordinary fight in theoretical physics over whether information can ever truly be destroyed. The third is entropy and the thermodynamic arrow of time, and what physics actually says about the experience of time ending. And the fourth is cosmology and deep time, and what happens to the concept of identity when you zoom out to the scale at which physics does its most extreme thinking. Each of these pillars removes one intuitive assumption about what death does. By the time we have walked through all four, the folk model, the simple, intuitive, terrifying idea that you exist and then you stop existing, will have been quietly dismantled from four different directions simultaneously. And you will be left with something that is not reassuring in any simple way, but that is genuinely strange, genuinely worth sitting with, and genuinely what the physics says. The universe transforms. It does not delete. Let us find out what that actually means. Part 5. The block universe enters quietly. Here is the part where physics starts pulling on a thread most people never notice is there. It starts with a simple observation that Albert Einstein made in 1905 at age 26, working as a patent clerk in Bern, Switzerland. Light travels at a fixed speed through a vacuum, approximately 299,792,458 meters per second, and this speed does not change depending on how fast the observer is moving. That observation, banal on the surface, turned out to have consequences so extreme that even Einstein spent years working through their implications. One of the most profound: there is no universal present moment. None. Not anywhere in physics. Think about what now means in everyday experience. It means the current moment, the thin sliver of time that separates past from future, the moment where you are. It feels like a fact about the universe, that there is a global present, that at this moment everywhere in the cosmos, everything is happening simultaneously. But special relativity destroys this intuition completely. Because of the finite speed of light, two observers moving at different velocities will disagree systematically, mathematically, correctly about whether two distant events happened at the same time. There is no observer-independent fact about simultaneity. Now is not a feature of the universe. It is a feature of your reference frame. This means time is not a river flowing forward, carrying all of reality with it. Time is a dimension, a coordinate, the same kind of coordinate that up, down, or left, right is. And just as the distinction between north and east is not a fundamental feature of the universe, but depends on how you orient yourself, the distinction between past and future, from the perspective of the equations, is far less absolute than experience suggests. When you combine space and time into a single four-dimensional structure, which is what Hermann Minkowski showed was the natural mathematical framework for special relativity, you get something called spacetime. And in spacetime, events are not things that happen and then cease. They are points, coordinates in a manifold. Every event that has ever occurred, the formation of the sun, the first moment of your life, this moment right now, has a location in that four-dimensional structure, not a former location, a location, present tense. The geometry does not have a past shelf and a present shelf and a future shelf, with events being moved from one to another as time progresses. The geometry simply contains all events. This is called the block universe, or eternalism, and it is the most straightforward interpretation of the mathematics of relativity. Not a fringe idea, not a minority view, but the interpretation most directly implied by taking the equations seriously. The universe, in this picture, is a static, four-dimensional object. What we experience as the flow of time, the sense of moving from moment to moment, of the present being real in a way the past and future are not, is something happening inside the structure not something the structure itself is doing. And this changes what death looks like. If time is a dimension, and all events in that dimension coexist in the geometry, then the last moment of your life is not a transition into nothing. It is a boundary in a structure, the end point of a world line, and boundaries in geometric structures do not cause the structure to disappear. The end of a road does not unmake the road. The edge of a continent does not mean the continent is not there. This is not metaphor. This is the mathematics. And it gets even stranger when you look at what it means for a human life specifically. Part 6. Your entire life as a geometric object. Your life, in the framework of relativity, is a world line, a continuous curve through four-dimensional spacetime, tracing every position you have ever occupied at every moment you have ever existed. From birth, from conception, really, depending on where you draw the boundary, through every second of your life, through this moment right now, and extending forward to the final moment of your biological existence. That entire curve exists as a feature of the space-time manifold, not the past parts as memories, and the future parts as anticipation, and the present part as reality, the whole thing, at once, as a geometric object. Your birth is a point on that curve. Your death is another point on that curve. Neither is more or less real than any other point. They all coexist in the structure. The moment you are 10 years old, sitting somewhere doing something you may not even remember, that moment is not gone. It is embedded. It is a coordinate. If you could somehow stand outside of time, outside of the four-dimensional structure, and view it the way you can view a three-dimensional sculpture, you would see your entire life laid out as a single object, all of it present simultaneously. This is a thought experiment that tends to either fascinate or disturb people, often both simultaneously, and that reaction is worth examining, because the instinct is to protest, to say, but the past is gone. My 10-year-old self does not exist anymore. Those moments are over, and the response from the physics is quietly devastating. Those are your experiences from inside the structure. Those are what it feels like, from within a consciousness embedded in the world line, to move along the dimension of time. The feeling of the past being gone is real as a feeling. The physics says the events themselves are not gone. Consider what happens at the end point of the world line, the moment of death. In everyday thinking, that moment has a special quality. It is not just a moment like other moments. It is the last moment, the one after which there are no more moments. It feels fundamentally different from any other point on the world line. But in the geometry of space-time, it is just another coordinate. There is no equation in general relativity that treats the end point of a world line differently from any other point on that world line. The manifold contains all points equally. The geometry does not register that this particular point is a terminus in any ontologically significant sense. It is a boundary, in the mathematical sense of a boundary, the same way that the last page of a book is a boundary, while the book itself, all of its pages together, remains entirely present as an object. There is an analogy that helps here, though all analogies eventually break. Think about the difference between reading a book and the book existing as a whole. When you read a book, you experience it page by page, one word following another, earlier pages becoming past and later pages remaining future, only the page in front of you feeling present. From your perspective as a reader, the book unfolds in time, but the book itself, as an object, contains all of its pages simultaneously. The last page is already there, whether you have read it or not. The existence of the last page does not diminish the existence of any other page. They all coexist in the object. Your life, according to the block universe, is like that book. From the inside, from the perspective of the consciousness embedded in the world line, it unfolds in time. Each moment follows the last. The past recedes, the future approaches, the present is the only real thing. But the book is already written. The world line is already a complete object in the manifold. Every moment of your life, Every conversation, every sensation, every mundane Tuesday morning is already there, already a permanent feature of the four-dimensional structure. And death, from this perspective, is not the end of the book. It is the last page. The page that was always going to be there, that is there, in the structure, the same way every other page is there. The structure does not become less real when you reach the last page. It does not vanish. It is complete. Now, the question this raises immediately is enormous. Does this mean anything for experience? Does it matter, in any lived sense, that your past moments are still there in the geometry of spacetime? And this is where the physics runs into its limits, where it hands the question off to philosophy and stands quietly at the boundary. The physics says the events are preserved in the structure. It does not say consciousness can access them. It does not say experience continues. It is not offering you immortality or comfort. It is offering you something stranger. The suggestion that gone is not a physics word. That erasure is not a physics operation. That the universe, as far as the equations of relativity are concerned, does not erase your life when it ends. It retains it as geometry. And what you do with that fact, what it means for how you think about mortality, meaning, loss, is entirely up to you. Part 7. The Einstein letter that changes how physicists talk about time. In March of 1955, Albert Einstein was 76 years old, living in Princeton, New Jersey, and aware that he was dying. His health had been failing for years. And in that month, he received word that Michel Besso, his closest and oldest friend, the man who had been his sounding board during the development of special relativity 50 years earlier, had died in Geneva. Einstein wrote to Besso's family. The letter is short. It is warm, and it is grieving in its own way, and near its end it contains a sentence that physicists and philosophers have been returning to ever since. Einstein wrote that Besso had preceded him by a little, and that this meant nothing, because, Einstein wrote, the distinction between past, present, and future, however stubbornly persistent, is an illusion. Now, this sentence has been quoted many times, often in contexts that make it sound like the gentle philosophizing of an old man. But Einstein was not speaking loosely. He was a physicist to his core, and he was speaking in the strict language of the framework he had spent his life building. He meant it technically. The distinction between past, present, and future is not a fundamental feature of physical reality. It is a feature of experience, of the way conscious beings embedded in the world line perceive their motion through space-time. The block universe, the four-dimensional manifold in which all events coexist, was Einstein's universe. And in that universe, Besso's death was not a deletion. It was a point in a structure. A point that existed permanently alongside every other point on Besso's world line, and alongside every point on Einstein's world line, where they had worked together, argued together, thought together. Einstein died 1 month later, in April of 1955. He died having built a framework for physics that, by its own logic, preserved both of them as geometric features of the universe, not their consciousness, not their experience, but the events of their lives, every moment, every point on their world lines, permanently embedded in space-time. The emotional weight of this should not be missed. Here is a man, one of the greatest scientists who ever lived, approaching his own death, writing to the family of his dead friend, and deploying his own theory to reframe that death not as disappearance, but as relocation in a structure that does not delete. That is not a comfort, exactly. It offers nothing about experience or consciousness or reunion. But it is a genuine statement about physics, and it reinforces the thread running through everything we are discussing, that the universe, as described by the equations, does not have a deletion mechanism. It has geometry. It has states that evolve. It has structure that persists. The fact that Einstein felt this was worth saying precisely at that moment, to people in grief suggests that even for the physicist who built the theory, the gap between the mathematical description and the lived experience of loss was something that needed bridging. He was not claiming Besso survived. He was claiming the universe does not erase. And those two claims are different in important ways that we are still working through. What does it mean for how you think about the people you have lost, to know that their moments, not their consciousness, not their experience, but the events of their existence, are permanent features of a geometric structure? What does it mean for how you think about your own eventual death? These are not questions with clean answers. They are questions worth carrying, and the rest of this discussion is going to give you more pieces to think about. Part 8. The frozen river and its limits. The frozen river metaphor is one that physicists and science writers sometimes reach for when trying to explain the block universe to people encountering it for the first time. Imagine a river. Now imagine it frozen solid, not in motion, not flowing, but static, the entire length of the river present at once. The water upstream and the water downstream and the water right in front of you are all simultaneously there, all part of the same structure. You can point to any section of the frozen river and it is just as real as any other section. The beginning and the end of the river coexist in the frozen structure. The analogy works as a first approximation. It captures the idea that time in the block universe is not flowing, that all moments coexist, that the past is not receding into non-existence, and the future is not yet to be created. The frozen river is all there at once, the way spacetime is all there at once. But the analogy collapses under scrutiny, and it is worth understanding where it collapses, because the failure points reveal something important. A frozen river is still a three-dimensional object that you, the observer, are viewing from outside, standing on a bank, able to see its full extent. You are not inside the river. You are not a frozen section of the ice, experiencing the other sections. In the block universe, you are the ice. You are a section of the structure, embedded in it, moving along it, or rather, perceiving yourself to be moving along it, unable to stand outside and view the whole thing the way you view the frozen river. And this is where visualization becomes genuinely impossible, because humans cannot visualize four-dimensional objects. Our brains build three-dimensional models of the world, and that is as far as our spatial intuition extends. The mathematics of a four-dimensional space-time manifold does not depend on our ability to visualize it. The equations work whether or not any human mind can form a mental image of what they describe. And this is a deeply important point for how we approach physics in general. The universe does not organize itself around what the human nervous system finds comprehensible. The universe operates according to its own rules, and some of those rules produce structures that are fully specified mathematically but effectively invisible to unaided human intuition. So the frozen river captures something. It captures the simultaneity, the all-at-once nature of the block universe. But it fails to capture the embedding, the fact that we are not external observers of the structure, but internal features of it. And it fails to capture the four-dimensional nature of spacetime, which does not have a good three-dimensional analogy because it is genuinely different in kind from any three-dimensional object. What it does preserve, and what matters for our central question, is the basic point. Nothing in the frozen river disappears. The upstream section does not cease to exist because you are standing near the downstream section. The downstream section is not yet real because you cannot see around a bend. Every part is there. And that is the feature of the block universe that bears directly on death. That is the feature Einstein was reaching toward in his letter. That is the feature that quietly undermines the intuition that dying means ceasing to be part of the universe. The universe, in the relativistic description, does not perform deletions. It contains structure. Your life is structure. And structure, in geometry, persists. Part 9. Quantum mechanics refuses to forget. Shift from geometry to information. from the language of spacetime to the language of quantum theory. And in quantum theory, the principle at the center of everything is called unitarity. And unitarity is, at its core, a statement about memory. The universe, at the quantum level, does not forget. Here is what unitarity means. The Schrödinger equation, the master equation governing how quantum systems evolve in time, is linear and unitary. Unitary means it preserves a mathematical quantity called the norm of the wave function, and more importantly, it means the evolution is reversible in principle. If you know the exact state of a quantum system at any moment, and you know the Hamiltonian governing its evolution, you can run the equations forward to find any future state, and you can run them backward to reconstruct any past state. No information is lost in the process. The total information content of the quantum state is conserved, the way energy is conserved. Quantum evolution is perfect bookkeeping. Now, why does this matter? Because information, in the physical sense, is not an abstract concept. It is a property of physical systems, the number of distinguishable states a system can occupy, the correlations between different parts of a system, the structure that distinguishes this configuration from every other configuration. And when something complex, say a human body, a brain, a mind, undergoes a transition, quantum unitarity says that the information content of the system is conserved in the total state of the universe. The information gets redistributed. It gets scrambled. It gets encoded in correlations between the atoms that used to be you and the atoms of the air and soil around you and the photons radiating outward from the heat of your decay. But it is there, all of it, perfect conservation. There is a distinction that matters enormously here between scrambling and deletion. Scrambling is what happens when you take a neatly organized message and encrypt it, or shred it, or mix it into a pile of random paper confetti. The information is still there, in principle. With perfect knowledge, you could reconstruct it. But in practice, it is completely inaccessible. You cannot recover the message from the confetti without extraordinary effort or extraordinary technology. Deletion would be if you somehow removed the confetti from reality entirely. Quantum mechanics allows scrambling. It forbids deletion. This means that the physical information constituting you, the specific quantum state of every atom in your body, the correlations that encode your memories and personality and neural structure, is not destroyed when you die. It is scrambled. It is distributed across the environment in a form that no conceivable practical technology could decode. But physically, mathematically, within the framework of quantum theory, it is there. The universe is maintaining its books. This is the informational face of the same insight we found in classical mechanics and in relativity. The universe's laws, across every framework we have, are transformation laws. They describe how information moves and changes form. They do not describe the creation of information from nothing, and they do not describe the destruction of information into nothing. The universe appears to be informationally closed, a system in which everything is conserved, in which the total state always contains everything that ever was, encoded in ever more complex correlations. And the question of whether this holds in all cases, whether there is any physical process that genuinely destroys information, is one of the most contested and important questions in modern theoretical physics. The most severe test of the principle came from the most extreme objects in the universe. Part 10. The black hole paradox that almost broke physics. In the mid-1970s, Stephen Hawking published a calculation that shook theoretical physics to its foundations. He had combined general relativity with quantum field theory, two frameworks that do not sit comfortably together, two frameworks whose unification is still one of the central unsolved problems in physics, and applied them to black holes. And the result he found was both extraordinary and deeply troubling. Black holes, in general relativity, are regions of spacetime where gravity is so strong that not even light can escape. Once something crosses the event horizon, the boundary of no return, it is gone from the external universe's perspective, sealed away from any communication with the outside. Hawking's calculation showed that quantum effects near the event horizon cause black holes to radiate, to slowly emit energy in the form of thermal radiation, random in character, carrying no information about what fell in. Over an enormous span of time, the black hole loses energy, shrinks, and eventually evaporates completely. And in Hawking's original calculation, everything that had ever fallen into the black hole, all of that information, all of those physical states, would be gone, permanently destroyed, not scrambled, deleted. This was a crisis, not a philosophical puzzle, but a genuine crisis, because if information can be destroyed by black holes, then quantum mechanics must be wrong. Specifically, unitarity must be violated. The foundational principle that physical evolution preserves information must fail. And if unitarity fails, the entire framework of quantum theory, which underlies all of modern physics, from the transistors in computers to the chemistry of biological molecules, would require fundamental revision. The fight that followed this calculation is one of the most extraordinary in the history of physics. It lasted decades. It drew in the greatest theoretical physicists on the planet. On one side, Hawking and others who believed information loss was real, that the universe could delete. On the other side, physicists like Leonard Susskind and Gerard Hooft, who were convinced that unitarity could not be wrong, that information had to be preserved somehow. Susskind later wrote a book about this fight called The Black Hole War, and the conflict was real and personal and technically brutal. What eventually emerged from this fight, and which Hawking himself ultimately conceded in 2004, revising his original position, was a picture in which information is not lost. The Hawking radiation coming out of an evaporating black hole is not truly random. It is not truly thermal. It is correlated in extraordinarily subtle ways with the precise quantum state of everything that ever fell into the black hole. The correlations are so complicated, so spread across so many degrees of freedom, that extracting the information would be effectively impossible for any realistic observer. But it is there. The total quantum state of the universe, including the radiation from an evaporated black hole, contains the complete information record of everything that ever fell in. The universe did not forget. It just made the memory incomprehensibly hard to read. This means that not even the most extreme objects in the known universe, black holes, which were specifically designed by the equations of general relativity to trap and seal away everything that approaches them, are capable of deleting information. The universe's commitment to conservation is that fundamental, that absolute. And this connects back to our central thread in the most direct way possible. If black holes cannot delete information, nothing can. The process of dying, of biological decomposition, of the atoms that made you scattering into the environment, this is a scrambling process, an information redistribution process, exactly like Hawking radiation. Extraordinarily difficult to reverse in practice, functionally impossible to read back, but not deletion, never deletion. The universe, even in its most extreme behavior, never writes a delete command. It only transforms. Part 12. The modern resolution, stranger than expected. The resolution to the black hole information paradox did not arrive in a single paper or a single moment. It accumulated over decades of work, and its most sophisticated form involves ideas that were barely imaginable at the time of Hawking's original calculation. The most important of these is the holographic principle. The holographic principle, developed most influentially by Jacob Bekenstein and Stephen Hawking themselves, in the context of black hole thermodynamics, and later generalized by Tooft and Susskind, makes the following startling claim. The information content of a region of space is not proportional to the volume of that region, but to its surface area. A region of space with a boundary of area A can contain at most a specific maximum amount of information, regardless of how much volume is enclosed. The universe behaves as if all of the information describing a three-dimensional volume of space is encoded on the two-dimensional surface surrounding it, like a hologram, which encodes three-dimensional image information in a two-dimensional film. This idea was placed on precise mathematical footing by Juan Maldacena in 1997 through what became known as ADS CFT correspondence, one of the most cited papers in theoretical physics. The correspondence shows that a specific type of quantum gravity theory in a particular higher dimensional spacetime is mathematically equivalent to a specific type of quantum field theory living on the lower dimensional boundary of that space. Gravity in the bulk, quantum theory on the boundary. The two descriptions are dual, different languages describing the same physical reality. Why does this matter for information? Because it means the universe has a backup. Everything happening in the interior of a region of spacetime is encoded in correlations on the boundary. Information does not merely live in the local degrees of freedom of physical matter. It is distributed non-locally, across the boundary, preserved in a form that might be inaccessible in practice, but is structurally indelible. Recent work, particularly results involving the Page curve and quantum extremal surfaces, developed in the late 2010s and early 2020s, showed how this framework resolves the specific calculation that troubled Hawking. The information in Hawking radiation does come out. It comes out encoded in subtle quantum correlations between early and late radiation, correlations that can only be detected through a technology so advanced it makes any current capability look rudimentary. But the information is genuinely there. The Page curve, a specific prediction for how information should come out of an evaporating black hole if unitarity is preserved, matches what the holographic framework predicts. The universe keeps its books. And what this means, brought back to the question we are actually asking, is that the universe is more like a perfect encryption system than like a filing cabinet with a shredder. When information enters a black hole, or when a complex organism dies and decomposes, the information is not shredded. It is encrypted so thoroughly that the encryption might as well be permanent from any practical perspective. But encryption is not deletion. The cipher exists. The information is there, distributed in the quantum state of the environment, the radiation, the subtle correlations between every particle that was ever in contact with the system. You, as information, are never lost. You are just encoded in a language so complex that the universe itself would need infinite resources to decode it. Part 13. The unsettling implication. Here is where this gets philosophically difficult. The conservation of information is a fact about physics. A physical system's information content is preserved in the total quantum state of the universe. That is what the mathematics says, and that is what the black hole information paradox forced physicists to confirm at enormous intellectual cost. The universe does not delete. But conservation of information is not the same thing as continuity of identity, and this distinction is crucial. The information that constitutes you, the quantum state of your atoms, the correlations that encode your memories and personality, is conserved after death. It is distributed. It is scrambled. It is spread across the environment in forms utterly unrecognizable as you. But the bits are all there. The universe has, in some technical sense, not lost a single one of them. What the universe has lost, what does not survive, is the integration. Identity, as you experience it, is not just a collection of information. It is organized information, structured information, information processed and integrated in a specific way by a specific architecture. The neural network that is your brain is not just a vessel for information. It is an information processing structure, and the processing itself, the integration, the moment-by-moment binding of sensory input and memory and prediction into a coherent experience of selfhood, that structure requires a functioning architecture. When the architecture breaks down, the processing stops. The information persists, scattered in the environment. But the integration, the thing that made it experience, the thing that made it you, that requires the structure to be intact. So physics gives you something extraordinary and something terrible simultaneously. The extraordinary thing: you are never, at the level of information, erased from the universe. Every bit of you is conserved, exactly and perfectly, in the total quantum state of reality. The terrible thing: those bits, scattered across the environment, bear no functional relation to the self you experience as continuous. Conservation of information is not conservation of consciousness. Conservation of information is not conservation of identity. It is conservation of the raw material, the way a demolished building's bricks still exist after demolition. The building is gone. The bricks are still there. And this is exactly the gap in physics, the gap we keep circling back to. Physics says transformation without deletion. Experience says there is something it is like to be you, right now, and that this something will cease. Physics is not equipped to adjudicate between these two accounts. It can tell us the information is conserved. It cannot tell us whether information conservation is enough for the thing that matters, the continuity of experience, the survival of the self in any felt sense. That question sits at the boundary between physics and philosophy, exactly where the hard problem of consciousness lives, exactly where our current understanding runs out. But we are not done, because there is another dimension to this question, the dimension of time, the arrow of experience, the direction that thermodynamics gives to the universe, and it adds something genuinely strange to the picture we are building. Part 14. Life as a low-entropy island. The second law of thermodynamics is the one law of physics that seems to point in a definite direction. In a universe where almost everything else is time-symmetric, where the equations of mechanics and quantum theory work equally well running forward or backward in time, the second law insists on an asymmetry. Entropy, the physicist's measure of disorder, always increases over time in a closed system. Order spontaneously dissolves into disorder. Heat flows from hot to cold, never the reverse. Complex structured systems drift towards simpler, more diffuse states. This is the law that gives time its arrow. The reason you remember the past and not the future. The reason broken glass does not reassemble itself. The reason age moves in one direction. The second law is, in a sense, the law that creates time's direction as we experience it. And it makes life, any life, not just human life, something remarkable. Life is a local violation of the second law's tendency. Not a genuine violation. Thermodynamics is not wrong, but a temporary, local, energy-maintained exception. A living organism takes in energy from its environment, sunlight for plants, chemical energy and food for animals, and uses that energy to maintain its internal order, to keep the complex organized structure of biology from dissolving into equilibrium with the environment. Life is, in thermodynamic terms, an island of low entropy in a sea of increasing disorder. Your brain is the most extraordinary example of this. The human brain, consuming about 20 watts of electrical power, roughly the power of a dim lamp, maintains a structure of almost incomprehensible complexity. Roughly 86 billion neurons, connected by approximately 100 trillion synaptic connections, firing in coordinated patterns of electrochemical activity that encode sensation, memory, prediction, emotion, language, identity. This level of organization, maintained constantly against the thermodynamic gradient, is what makes consciousness possible. The brain is a low-entropy engine running on a steep energy gradient, and it produces experience as its output. Death, from the thermodynamic perspective, is what happens when that engine fails. When the energy supply is cut, or the maintenance mechanisms break down, the structure begins to dissolve. Entropy increases. The ordered patterns of neural activity, the coherent waves of electrical signal, the coordinated dance of neurotransmitters, the carefully maintained concentration gradients across cell membranes, all begin to relax toward equilibrium. This is not an instantaneous event. It is a process, unfolding over minutes and hours and days, as different systems fail at different rates. The precise orchestration of biological chemistry, which life spent billions of years of evolution perfecting, unwinds. And here is the thing worth noting, the thing that connects this back to the question of whether death is deletion. When a low entropy structure dissolves into a higher entropy state, the matter and energy of the original structure do not disappear. They redistribute. The atoms of your brain do not cease to exist when neural activity stops. They disperse into the environment, participating in other chemical reactions, other biological processes, other configurations. The energy that was maintaining your neural order becomes heat, becomes the chemical energy in soil bacteria, becomes the kinetic energy of decomposition gases. The ordered structure is gone. The stuff making up the ordered structure is entirely present, differently arranged. This is the thermodynamic version of the same argument we made in the first act. Entropy's arrow does not point toward deletion, it points toward redistribution. The universe is not emptying itself. It is homogenizing itself, spreading its contents more evenly. And in that spreading, nothing is lost from the inventory of matter and energy. Only the structure, the organization, the pattern, the improbably low entropy arrangement that was a life, dissolves. Part 15. Death as loss of structure maintenance. There is a tendency, when thinking about death, to imagine it as a single moment, a threshold, an event. The heart stops, the brain stops. There, that is the moment. Before, life. After, death. The switch position changes, but thermodynamics does not support this picture. Death is not a switch, it is a process. And the process is the gradual, cascading failure of the body's ability to maintain its own order against the thermodynamic gradient. Consider what happens in sequence. The heart stops, cutting off the oxygen supply to the brain. Within about 4 to 6 minutes, the neurons begin to fail. The sodium-potassium pumps that maintain the electrical gradients across cell membranes require energy, and without it, those gradients collapse. The organized patterns of electrical activity that characterize a functioning brain, the rhythms and oscillations that correlate with consciousness, with memory, with all the functions of mind, give way to a brief burst of disorganized activity and then to silence. The electrical architecture of the brain dissolves, but the atoms are still there. The proteins, the lipids, the nucleic acids, the neurotransmitter molecules, all of the chemical constituents of the brain remain. Over hours and days, enzymatic processes break them down. Over weeks and months, decomposition organisms consume and redistribute them. Over years and decades, the atoms that compose the brain return to the soil, the water, the atmosphere. They enter other biological cycles. They become part of other organisms, other structures, other chemical configurations. At no point in this process is any matter or energy deleted. At no point is any information in the quantum sense destroyed. What is lost, irretrievably, practically, for any purpose that matters to us, is the specific organization, the particular arrangement of atoms that processed information in the specific way your brain processed information, the pattern that supported your experience, the structure that integrated the information into something coherent and continuous. And this raises a profound question about what identity actually is. If you are not your atoms, because your atoms are constantly being replaced throughout your life, as biological turnover replaces essentially every molecule in your body every few years, and if you are not your information content in the abstract, because information conserved but scattered bears no relation to you, then what are you? The answer that seems to follow from the physics is, you are a pattern, a process, a specific way of organizing and processing information that persists over time, not because any particular substrate persists, but because the organization itself is maintained continuously by the ongoing activity of the system. When that ongoing activity stops, the pattern dissolves, not into nothing, into dispersed, unintegrated components, the bricks of the demolished building, the encrypted text of the scrambled message. Physics does not describe the dissolution as deletion. It describes it as reorganization into a less structured state. But the pattern, the specific dynamic organization that was a mind, that is genuinely gone, not hidden, not preserved elsewhere. Gone as a pattern, even as its components persist. And this is the most honest thing we can say about what death does at the thermodynamic level. It does not delete, but it does dissolve. And dissolution, while not deletion, is its own kind of ending. The question is whether the end of the pattern is the end of the thing that mattered. Part 16. Observer-dependent arrow of time. This part enters genuinely speculative territory, and it is worth flagging that clearly. The ideas discussed here are not settled physics. They are active research directions, explored by serious physicists and philosophers of physics, but without anything like consensus. I am not presenting this as established fact. I am presenting it as a genuinely interesting, open question that bears directly on what death means at the physical level. The question is this: is the thermodynamic arrow of time the direction in which entropy increases, the direction we experience as forward, something that exists independently of observers? Or is it, in some important sense, something that is defined by information processing systems? The standard answer is that the arrow of time is objective. Entropy increases in the universe because the early universe started in an extraordinarily low entropy state, something cosmologists call the past hypothesis, and has been evolving toward higher entropy ever since. This is independent of whether any observer is present to notice it. But a more subtle view, developed by researchers including Carlo Rovelli and others working at the intersection of quantum gravity and thermodynamics, suggests that the distinction between past and future, the thermodynamic asymmetry that gives time its direction, is closely tied to the perspective of physical systems that interact with and remember the past. In this view, the arrow of time is not simply a feature of the universe's global state. It is a feature of how information flows between physical systems, of which way the correlations run, of what a given system can predict about its future versus what it retains as memory of its past. If this is right, and again, this is speculative, then the experience of time as flowing in a direction is intimately connected to the existence of a physical system that processes information in the thermodynamically asymmetric way. Memory requires that the system's past interactions leave traces in its current state. Prediction requires that the system's current state allows extrapolation to future states. Both require an information processing system operating in a thermodynamically asymmetric environment. And when that system stops, when the brain no longer maintains the energy flow and information processing that supports experience, the thermodynamic arrow, as experienced, ends. Not because the universe stops having a thermodynamic arrow, the universe continues. Entropy continues to increase. But the particular experience of time's direction, the subjective sense of flowing forward from moment to moment, requires a functioning observer. When the observer stops, the observer's experience of time stops. This is a way of saying something about death that physics can approach without claiming to fully answer. From the outside, death is a physical process, the breakdown of a low entropy system, the dispersal of its components, the continuing increase of entropy in the broader universe. From the inside, if there is an inside, the thermodynamic arrow that organizes experience ends, not because time ends, but because the machinery that makes time experienceable has stopped running. Part 17. The Last Moment Paradox. There is a strange logical problem lurking at the edge of any attempt to describe the last moment of experience. Try to describe what happens when experience ends, from the inside. What does the last moment feel like? The problem is that answering this question requires you to survive beyond the last moment in order to reflect on it. But if you survive beyond it, it was not the last moment. The very act of describing what the last moment feels like presupposes that there is a moment after it from which the description is given, and there is not, by definition. This is not just wordplay. It has a genuine structural consequence. The last moment of experience cannot be experienced as the last moment. You cannot know, from within experience, that a moment is the last one. You can anticipate it. You can approach it. You can be aware that something is ending. But the moment of actual ending, the precise point at which experience becomes non-experience, cannot be witnessed from inside, because witnessing requires experience, and experience has ended. Physics describes the process from outside. It describes the dissolution of neural coherence, the fading of coordinated electrical activity, the gradual breakdown of the brain's information processing architecture. This is the external description. But from inside, from the perspective of the first-person experience that was associated with that brain, there is no description of the ending, because descriptions require experience, because you cannot report on your own non-existence. There is something here that resembles the experience of falling asleep. You have fallen asleep thousands of times in your life, and yet you have never experienced the moment of falling asleep. You have been awake, and then you have been asleep, and there is no memory of the transition, because memory requires a conscious brain to record it, and the moment of sleep onset is precisely the moment at which consciousness is suspended. The transition is invisible from inside. Death may be structurally similar, but permanent. Not a transition to another state of experience, sleep, dream, waking, but a transition to no further experience at all. From inside, there would be experience, and then there would be the absence of experience. But the absence of experience is not itself an experience. It cannot be felt. It cannot be witnessed. It cannot be described from within. Physics can describe the system from outside. The system cannot describe itself from inside after the system stops. And this is perhaps the strangest and most important thing physics has to say about death. Not that it is terrible, not that it is nothing to worry about, but that it is, by construction, invisible from inside. The ending that we spend so much of our lives dreading is the one event in our existence that we cannot, even in principle, experience as ending. We can experience everything leading up to it. We can experience the approach. We cannot experience the arrival, because the experience and the ending are, by definition, mutually exclusive. Part 18. Deep Time and Recurrence Physics. Scale up, way up, far beyond the human scale, far beyond the biological scale, far beyond the scale of civilizations or species or planets or even stars. Go to the scale where physics thinks about the long-term behavior of the universe itself. And at that scale, something extraordinary happens to the question of identity and recurrence. In 1890, the French mathematician Henri Poincaré proved a theorem about the long-term behavior of classical physical systems. The theorem applies to systems with a finite number of states confined to a bounded region of phase space, and it states the following: such systems will, given sufficient time, return arbitrarily close to any state they have previously occupied, not exactly, but to within any specified degree of approximation. Every configuration the system has ever been in will be revisited, infinitely often, over infinite time. The system is fundamentally recurrent. The timescales involved are staggering. For a system with the complexity of a human body, roughly 10 to the power of 28 atoms, the Poincaré recurrence time, the average time before the system returns to within microscopic proximity of its original state is a number so large it would require many pages just to write out in decimal notation. It dwarfs the current age of the universe by factors that make the current age of the universe look like a rounding error. 10 to the power of 10 to the power of 28 years, roughly. A number that makes eternity seem quaint. There is also the important caveat that the theorem applies to classical mechanical systems, and the universe may not satisfy all of its assumptions. It may be expanding indefinitely in ways that change the relevant phase space structure. The theorem is a mathematical result that applies cleanly to idealized systems, and whether it applies to the actual universe is a legitimate question with no settled answer. But here is what is interesting about the result, even as a mathematical statement about idealized systems. It says that in a universe with finite resources and infinite time, configurations recur. The specific arrangement of matter and energy that constitutes any particular state, including, in principle, the state that was a human brain at a particular moment, is not a one-time event from the universe's perspective. It is a sample from a distribution of possible configurations, and given enough time, the distribution will be sampled again. This is not a promise. It is not a prediction. It is a mathematical consequence of the laws of classical mechanics applied to closed systems over infinite time, and it reinforces the central thread in the most extreme way possible. The universe does not delete configurations. It samples configurations, and given infinite time, it resamples them. The specific arrangement of atoms that was U is not gone from the universe's possibility space. It is a point in configuration space that the universe, if it runs long enough, and if the right assumptions hold, will visit again. Part 19. Boltzmann brains and statistical observers. Ludwig Boltzmann, the 19th century Austrian physicist who pioneered statistical mechanics, thought harder about the long-term statistical behavior of physical systems than almost anyone before or since, and his thinking led him to a deeply unsettling place. If the universe is a statistical system with a finite number of states, and if it evolves for long enough, then sufficiently rare thermal fluctuations become inevitable, including fluctuations that, purely by chance, briefly assemble structures of arbitrary complexity, including, in principle, structures that briefly resemble a functioning brain, complete with apparent memories of a past that never happened. These hypothetical entities, called Boltzmann brains, are a genuine puzzle in cosmology. In an eternally expanding universe, or in a universe that undergoes eternal inflation, the probability of such random fluctuations is not zero. And if you average over all possible observers across cosmic time, the question of whether a typical observer is a coherent biological creature with a genuine past or a random fluctuation with false memories becomes philosophically disturbing. This is not a crisis for everyday physics, and there is no empirical evidence that Boltzmann brains dominate the observer landscape. But the fact that physics can even raise the question points to something important. Identity, in the physics picture, is a statistical event. Your existence as a coherent, memory-having, experience-having observer is not a metaphysically guaranteed feature of reality. It is a particular configuration of matter that arose through a specific causal process, one of an enormous number of possible configurations, significant from your perspective precisely because you are inside it. The universe does not assign it special status. What Boltzmann brains add to the picture is not despair but precision. They sharpen the distinction between physical conservation and identity continuity. The universe conserves information. It allows recurrence. It permits, in principle, the statistical reassembly of any configuration, but it does not privilege any particular configuration as the one that deserves to persist. It explores the configuration space with indifference. You are a region of that space that was occupied for a while. The universe does not particularly notice when you leave. Part 20. The reassembly of you. Poincaré recurrence says configurations return. Quantum information conservation says the information is never deleted. The holographic principle says the universe maintains its records. And it is tempting, following all of this, to draw a conclusion that sounds almost comforting. The specific configuration of matter and energy that was you will, given infinite time, reassemble. You will recur. In some far future epoch, the exact pattern will reform, and there will be something that, physically, is identical to you. But this is where the physics forces a careful and important distinction, one that philosophy has been grappling with long before physics made it technically precise. The distinction between replication and persistence, between identity and similarity, between a copy and a continuation. Imagine that in a trillion years, or in the incomprehensibly longer recurrence time, the exact configuration of atoms and fields that currently constitutes you reforms. The same atoms, in the same arrangement, with the same quantum states. Call this entity the recurrence. Is the recurrence you? The answer from physics is, the recurrence has the same information content you have. It is physically indistinguishable from you. Any measurement that could be made on the recurrence would yield the same result as a measurement made on you. But the recurrence is not causally connected to you. There is no continuous physical process linking your current state to the recurrence's state. There is an enormous gap of time between you, during which your information was distributed, scattered, scrambled, and then, through a sequence of fantastically improbable fluctuations, reassembled. The causal chain that makes you, you, the continuous thread of physical evolution connecting who you were an hour ago to who you are now, is not present. The recurrence is a fresh start. An identical fresh start, physically, but a fresh start. Most conceptions of personal identity require causal continuity. They require that the person who wakes up tomorrow morning be connected to the person who fell asleep tonight through an unbroken chain of physical causation. The same brain, the same memories, the same continuous biological process. A teleporter that disassembles you and perfectly reassembles you elsewhere, even if the output is atom for atom identical, raises genuine questions about whether the output is you or an exact copy of you. The recurrence is even further removed than a teleporter copy. It is separated by infinite time and utter causal discontinuity. So Poincaré recurrence is not resurrection, it is replication. Physically perfect replication, if the assumptions hold. But replication is not the same as persistence. The universe can produce your exact configuration again without having preserved you in any sense that the continuous self would recognize. The information is there. The organization can reform. The identity, defined by continuous causal chain, does not carry across the gap. This is not a sad conclusion, exactly, but it is an honest one. Physics conserves everything but continuity, and continuity is precisely what identity requires. Part 21. The cosmological discomfort. Stand back even further, further than the scale of a human life, further than civilization, further even than the species. Stand back to the level of cosmological probability. The universe, on any timescale that matters, does not have preferences. It does not assign value to particular configurations of matter. It explores the space of possible physical states with something like indifference, constrained only by the laws of physics, and the laws of physics do not include any term for this configuration matters more than others. There is no weighting function built into the Hamiltonian that favors complexity over simplicity, life over non-life, consciousness over the arrangement of dust. The equations that govern the universe are, in this sense, profoundly neutral. Your existence, the specific configuration that is you, the arrangement of matter that supports your experience and your identity, the precise electrochemical patterns that constitute your thoughts and memories and sense of self, is a region of configuration space that the universe happened to occupy for a particular stretch of time. That stretch of time is extraordinarily short by cosmological standards. Even a human lifetime of 100 years is incomprehensibly brief compared to the timescales on which cosmology operates. The universe, at its current age of approximately 13.8 billion years, has barely begun. The era of star formation will continue for trillions of years. Black holes will evaporate via Hawking radiation on timescales of 10 to the 83rd years or longer, depending on their mass. Set against these numbers, the span of a human life does not merely seem small, it becomes, in any rigorous mathematical sense, indistinguishable from an instant. And yet, the universe ran through that configuration. It landed there, briefly, before moving on. Over sufficient time, the universe's evolution erases the distinction between configurations that were once significant from a human perspective and configurations that were never occupied at all. There is no cosmic archive that says, this is where the interesting configurations were. There is no memorial at the location in configuration space that was once you. The configuration space is explored and re-explored, and the significance we assign to particular configurations, the enormous meaning we attach to the specific arrangement of matter that constitutes a person, a mind, a life, is not a feature of the physics. It is a feature of our perspective from inside. Consider what this means, taken seriously. The universe does not distinguish between the configuration that was you and the configuration that was a rock formation on a planet orbiting a star in a galaxy you will never observe. Both are regions of configuration space. Both were occupied. Both were, in the physical sense, equally real during the time they were occupied. The universe spent time in those configurations and then moved on from both. The rock formation does not have a philosophy about this. You do. That difference, the presence of a philosophy, the capacity to ask the question, is, from within the experience of having it, the most significant thing imaginable. From the cosmological outside, it is another configuration. This is not nihilism, not quite. Nihilism, in its strong form, claims that nothing matters. What we are doing here is something different, a genuine confrontation with scale. The universe is not designed for human significance. Its laws conserve information and allow recurrence and preserve events in space-time geometry, all of which, when examined carefully, constitutes a form of non-deletion. But non-deletion at the cosmological level is not the same as significance at the human level. The universe does not delete you. It also does not particularly care about you. These are both true simultaneously, and holding them together is genuinely difficult, perhaps the most difficult thing that a consciousness capable of understanding cosmology is asked to do. There is a version of this confrontation that collapses into despair. If the universe is indifferent, if your existence is a fleeting configuration in an incomprehensibly large possibility space, if the distinctions that feel most important from inside will eventually be erased without record or remainder, then why does any of it matter? This is the natural first response, and it deserves to be taken seriously rather than immediately patched over with reassurances. The despair is pointing at something real. It is pointing at the genuine asymmetry between the weight of subjective experience and the weightlessness of that same experience from the cosmological outside. But the despair is not the only possible response. Another response, not easier but perhaps more honest, is to notice that the conflict between the two perspectives is itself the most characteristic feature of being a conscious entity in a physical universe. You are, by some extraordinary accident of physics and chemistry and evolutionary history, a configuration of matter that can represent the universe to itself. You can build models of cosmological scales, You can calculate the timescales of black hole evaporation. You can understand, at least abstractly, what it means for your own existence to be negligible by those standards. No other known configuration of matter does this. The rock formation does not have this problem, and it does not have it precisely because it lacks the capacity that makes the problem arise. The capacity for cosmological perspective is the same capacity that generates cosmological vertigo. What the cosmological picture offers, when it is approached as an invitation rather than as a verdict, is a kind of radical perspective shift. From inside your life, your existence has enormous weight. Every moment is filled with significance, with meaning, with the felt importance of being here, of having preferences and relationships and experiences that seem, from within, utterly non-negotiable in their importance. From the cosmological outside, your existence is a fleeting configuration, a brief occupation of a point in an enormous configuration space, lasting a negligible duration relative to the timescales on which physics operates. Both of these perspectives are valid. Both describe the same reality from different scales, and the discomfort of holding them together simultaneously, the vertigo of moving between the human scale and the cosmological scale, is, perhaps, one of the most characteristic experiences of doing physics seriously. It is an experience that people who have looked carefully at the numbers do not easily forget. There is also something important in the direction of the asymmetry. The universe's indifference to you does not undermine the reality of your experience. It does not reach back in time and unmake the significance you found in your life while you were living it. The felt weight of existence is not a cognitive error to be corrected by cosmological perspective. It is a different kind of fact about the same universe, a fact not about configuration space, but about what it is like to be inside one of those configurations while it is being occupied. Physics describes the universe from outside. Experience describes it from inside. Neither description is more real. They simply cannot be translated into each other, and the failure of translation is not a failure of either. It is the gap that makes consciousness interesting as a subject at all. What you are left with, after the cosmological confrontation, is not certainty in either direction. You are not left with the comfortable assurance that your existence matters in some cosmic register. You are also not left with the bleak conclusion that it therefore matters not at all. You are left instead with a more precise understanding of the question. The universe does not delete you. Your existence is preserved in the physical record, in the ways we have been discussing, in the causal structure of space-time, in the information that your existence has irreversibly altered. But the universe is not waiting for you to come back. It is not monitoring the configuration space for signs of your return. It is simply continuing, transforming, running through its vast inventory of possible states, conserving its information, following its laws, producing, over unimaginable spans of time, configurations we cannot predict and would not recognize. You were one of those configurations. For a brief moment, less than a blink, in cosmological terms, the universe arranged itself into something that could look back at it, understand something of what it was, and feel the full weight of existing inside it. That is a strange and improbable thing. Whether it is a significant thing depends on which scale you are using, and the universe offers both scales without prejudging which one you should prefer, with or without you, across timescales that make the current age of the universe look like a prologue forever. Part 22. The Missing Equation of Death. Let us now bring all four pillars together and name what they have collectively built. This is the synthesis, the place where all the threads we have been pulling on arrive at the same knot. Each framework approached the question of what happens to a person from a different angle, using a different vocabulary, operating at a different scale, and yet they converge. Not because we forced them to, not because we selected the frameworks that agreed with each other and discarded the ones that didn't, but because the question itself, what does physics say about the persistence of things, turns out to have a surprisingly consistent answer across the full spectrum of our most fundamental theories. Relativity tells us that spacetime is a four-dimensional geometric structure in which all events coexist. The moments of your life are permanent coordinates in that geometry, not memories of events, not records of events, not echoes of events, the events themselves, woven into the fabric of what exists. The particular Tuesday afternoon when you were 7 years old and the light came through a window at a specific angle and you understood something for the first time, that moment is a coordinate. It is located in space-time. It is not gone. It has not been deleted. The geometry that contains it extends, equally and without preference, through all of time, past, present, and future, and the geometry does not revise itself. The last moment of your life is not a transition into nothing. It is a boundary in a structure, and boundaries do not unmake the structures they bound. The edge of a continent does not delete the ocean. The final frame of a film does not erase the frames that preceded it. 9. Space-time does not delete. It preserves events as geometry. Quantum mechanics tells us that the universe is an information-preserving system. Unitarity, the mathematical requirement that the total quantum state of the universe evolves through transformations that conserve probability, demands that no information is ever created or destroyed. This is not a peripheral feature of the theory, it is one of the load-bearing walls. The information that constitutes you, the quantum states of your atoms, the correlations that encode your neural structure, the entanglements that thread through the matter organized into your body and brain, is never destroyed. It is scrambled. It is redistributed across an enormous number of degrees of freedom, dispersed into the environment so thoroughly that no practical process could ever recover it. But scrambling is not deletion. The information is there, maintained in the total state of the universe, exactly as quantum bookkeeping requires. Quantum theory does not delete, it scrambles. Thermodynamics tells us that what death does is dissolve structure. The organized low entropy pattern that was a living organism, maintained by continuous energy flow, held far from equilibrium by the remarkable machinery of biological life, relaxes toward equilibrium when that flow stops. The matter redistributes. The energy disperses. The organization that was, by any measure, improbable and intricate and worth noticing, dissolves into the more probable configurations that thermodynamics prefers. This can feel, from the inside of grief, like an annihilation. The thing that was there is no longer recognizably there. But thermodynamics is precise about what it says and what it does not say. It says the structure relaxes. It does not say the matter and energy cease to exist. It does not say the information that was encoded in the structure is removed from the universe's ledger. The dissolving is a transition to a less structured state, fully consistent with and demanded by the laws of thermodynamics. And those laws are about transformation, not about deletion. Entropy does not delete. It disperses. And cosmology and deep time tell us that the universe explores configuration space over timescales that make human history look like a rounding error. Over those timescales, configurations recur. The specific arrangement of matter that was you is not a one-time event in the universe's statistical history, never to appear in any form again, written off and forgotten. It is a point in configuration space. The universe samples points in configuration space as it evolves. It has already sampled yours. The information content of that configuration, what made you that particular arrangement and not a different one, is preserved in the quantum state of the universe even after the configuration has dissolved. And whether through Poincaré recurrence on the most extreme timescales, or through the simpler fact that the laws governing this universe produced you once and are the same laws operating everywhere and always, the configuration space does not close. Cosmology does not delete. It echoes. 4 frameworks, 4 independent lines of reasoning, 4 different languages in which physics describes the behavior of matter and energy and information and time. And in not one of them, not one equation, not one operator, not one fundamental law does anything corresponding to erasure of a person appear. The folk model of death, the intuitive idea that dying means ceasing to exist, ceasing to be part of the universe's inventory, going from something to nothing, this model has no support in the fundamental physics. There is no mechanism, there is no law, there is no delete function buried somewhere in the mathematics, waiting to be invoked when a biological system crosses the threshold from living to not living. The universe does not have a delete function. It has transformation functions, and they conserve. This is the synthesis, and it is, if you sit with it carefully, a genuinely strange result. We did not set out to prove something comforting. We set out to ask what the physics actually says. And what it says, consistently, across frameworks developed independently by different people to explain different phenomena, is that the physical universe does not erase the things that happen in it. Events are permanent in spacetime. Information is conserved in quantum evolution. Matter and energy transform, but do not vanish. Configuration space is traversed and retraversed over cosmological time. These are not marginal claims. They are among the most thoroughly tested and deeply established features of our best physical theories. And yet you will die. Everyone reading this will die. Everyone who has ever lived has died, and the full force of that fact does not diminish in the slightest when you set it against the conservation laws. The biology is real. The grief is real. The loss is real, not as an illusion to be corrected by physics, not as a cognitive error to be dissolved by the right framework, but as a genuine feature of what it means to exist as a conscious being in a physical world. The experience of losing someone is not reducible to a misunderstanding about thermodynamics. The experience of facing your own death is not a confusion about unitarity that a careful reading of quantum mechanics could clear up. These experiences have their own reality, operating at a scale and in a register that physics does not directly address. The experience of dying from the inside will feel, as far as we can tell, as far as anyone who has studied the question seriously has been able to determine, like ending. The first-person experience of the world, the felt quality of being here, the continuous thread of consciousness that connects your present moment to your past and reaches forward into your anticipated future. That thread, physics has essentially nothing to say about whether it continues. Physics has drawn the map of transformation. It has described with extraordinary precision what happens to the matter, to the energy, to the information, to the quantum state. It has established that none of these are deleted. What it has not done, what it may be constitutionally incapable of doing, given that it is a third-person description of a universe that contains first-person experiences, is tell us what the transformation is like from inside. This is where the final mystery lives. Not in the physics, which is, in its own terms, clear, not in the conservation laws, which are, in their own terms, unambiguous, but in the gap between the third-person description and the first-person experience, between knowing that the information that constitutes you is preserved in the quantum state of the universe and knowing what, if anything, it is like to be that information after the structure that organized it has dissolved, between the map and the territory, between the equation and the experience. The most honest statement of where we are is this: physics consistently describes a universe that does not delete, but the universe's refusal to delete does not tell us whether experience continues. It does not tell us whether consciousness persists. It does not tell us whether there is anything it is like to be the scattered, scrambled information that used to be a person, distributed across the environment, encoded in correlations too diffuse to reconstruct, preserved in the quantum ledger of a universe that neither celebrates nor mourns, the configurations it moves through. Physics has given us something real. The framework of deletion, the idea that death means ceasing to be part of what exists, is wrong, or at least unsupported by any fundamental law we know of. That matters. It changes the shape of the question. But it does not close the question. The deepest uncertainty is not about whether you will be preserved. It is about what preservation, at the level of scattered quantum information in an indifferent universe, means for the thing that you most fundamentally are. Not a configuration of matter, but a point of view on it. That is where physics ends. And something else, philosophy, perhaps, or simply the lived experience of being a mortal thing in a universe that will not quite let you go, must take over. Part 23. The identity gap in physics. The physical variables at the disposal of physics are matter, energy, momentum, spin, charge, fields, wave functions, and spacetime coordinates. These are the building blocks of every physical description ever written. They describe everything the universe is made of, in every configuration the universe has ever been in, to every precision physics can currently achieve. They are extraordinarily powerful tools. They are, by any reasonable measure, the most accurate and far-reaching descriptions of reality that human beings have ever produced. With these variables, physics has predicted the behavior of subatomic particles to 11 decimal places, described the evolution of the universe from fractions of a second after the Big Bang, and mapped the geometry of spacetime around objects so dense that light cannot escape them. The track record is without precedent in the history of human knowledge. There is no variable among them for selfhood, none. No term in any Lagrangian, no coordinate in any phase space, no quantum number in any model of particle physics, no field in any quantum field theory that corresponds to the person who is having this experience. Take any textbook in any branch of physics. Search the index. You will find mass, spin, charge, entropy, energy density, probability amplitude, metric tensor. You will not find self. You will not find subject. You will not find the concept that is, from the inside of any human life, the most certain and immediate thing in the world. The fact that there is someone here having experiences, being something rather than nothing. The concept of identity, the concept of a continuous self, a subjective experience, a perspective that persists over time and has a history and anticipates a future, does not appear in the mathematical formalisms of physics. It is not that it appears in some obscure corner and is difficult to extract. It is not that it is encoded implicitly and needs a careful translation to recover. It does not appear. The equations are silent on the matter of who is reading them. One response to this observation is that it should not appear that physics is a description of objective reality from a third-person perspective, and that first-person identity is simply not the kind of thing physics aims to describe. On this view, the physics of a brain is a description of the behavior of matter organized in a particular way, the identity of the person whose brain it is, the continuous, integrated first-person perspective that unifies all that neural activity into something it is like to be, is not a further physical fact about the matter. It is a feature of the interpretation of that matter by the mind that is running on it. Physics describes the score. Identity is what it sounds like from inside the performance. The absence of identity from physics, on this view, is not a gap, it is just scope. Physics does not describe symphonies either, and no one considers this a deficiency in the theory of acoustics. But this response becomes uncomfortable when you push on it, because if identity is purely interpretive, if it is entirely a matter of how the matter is organized, and the physics of that organization is complete, then there should be no further question about what identity is or where it lives. And yet, there manifestly is. Neuroscience has made extraordinary progress over the past several decades in mapping the neural correlates of specific experiences. The patterns of activity associated with perceiving a particular color, recognizing a particular face, retrieving a particular memory, making a particular decision. The specificity and precision of these mappings is genuinely remarkable. But neuroscience has not identified a neural correlate of selfhood itself, of the binding of all these specific experiences into a single, continuous, first-person perspective, the sense that all of this is happening to someone, that the experiences are integrated rather than merely co-occurring. The machinery is there, generating experiences. The experience of being a self is there, undeniable from the inside. The connection between them, the explanation of why this particular arrangement of matter gives rise to something it is like to be, and specifically to be this, is not understood, not approximately understood, not understood in principle with the details still to be filled in, not understood at all in any fundamental sense. This is the neural version of the hard problem of consciousness, as the philosopher David Chalmers named it, and it is worth being precise about what makes it hard. The easy problems of consciousness, and they are only easy relative to the hard problem, not in any absolute sense, are the problems of explaining cognitive functions, how the brain processes information, integrates signals from different sensory systems, controls behavior, produces language, stores and retrieves memories. These problems are difficult in practice, but they are the kind of problems that neuroscience and cognitive science are equipped to address, because they are problems about the functional and physical organization of a system. The hard problem is different. It asks not how the brain performs these functions, but why performing them is accompanied by subjective experience at all. Why is there something it is like to see red, rather than merely a pattern of neural activity that discriminates red wavelength photons from others? Why does the information processing happen in the dark of objective function, or in the light of felt experience? Why is there a light at all? No one knows. This is not false modesty. It is not the kind of not knowing that will yield to a few more decades of well-funded neuroscience. It is a conceptual gap, a gap in our understanding of what kind of thing consciousness is, whether it is the sort of thing physical description can capture, whether the third-person vocabulary of physics and neuroscience is even in principle adequate to describe what is, by its nature, a first-person phenomenon. There are serious philosophers and scientists who think the hard problem will dissolve as neuroscience matures, that consciousness will turn out to be a kind of information processing, and the felt quality of experience will turn out to be nothing over and above the function. And there are serious philosophers and scientists who think this will never work, that the explanatory gap is not an artifact of our current ignorance, but a structural feature of the relationship between objective description and subjective experience. The debate is genuine and unresolved. This matters enormously for the question of death, because the question of whether you persist through death, whether identity survives in any sense that would mean something to you, requires knowing what identity actually is at the physical level. The answer physics gives to the persistence question depends entirely on what we decide identity consists in. If identity is simply information, a specific pattern of data encoded in the states of neurons, a particular configuration of physical variables, then the conservation of information that quantum mechanics guarantees might seem to offer something. The information pattern that was you persists, in principle, distributed into the environment, encoded in the correlations between particles, maintained in the total quantum state of the universe. The bookkeeping is balanced. The information is not gone. But as we have seen, conservation of information is not the same as continuation of identity. It is not even close to the same thing. Identity, as we experience it from the inside, is not merely the presence of information. It requires integration. It requires the information to be gathered into something, organized into a perspective, unified into a point of view. Scattered information is not a self. A library contains enormous amounts of information about human experience without having any experience itself. The molecules of water that were once part of your body, now dispersed into the ocean, carry, in the quantum mechanical sense, correlations that trace back to you. They do not constitute you. The information that makes you you is not sufficient for you to be you unless it is integrated in the right way, organized in the right structure, running in real time on the right physical substrate. And death dissolves the substrate. The information persists, in some attenuated physical sense, but the integration is gone. And if identity is something beyond information, if there is some aspect of consciousness, some feature of subjective experience that is not captured by the information theoretic picture, then physics is even further from being able to address the question than the conservation laws might suggest. Because then what persists, when information persists, is not even the relevant thing. The hard problem of consciousness opens the possibility that consciousness is not simply a form of information processing, that the felt quality of experience involves something that the physical picture does not and perhaps cannot describe, that the map of objective physical states is missing the territory of subjective experience entirely. We do not know which of these pictures is correct. We do not know whether consciousness is physical in the sense that everything it consists of could, in principle, be described by the variables of physics. We do not know whether the hard problem will turn out to be a dissolved pseudo-problem or a permanent boundary on what physical description can reach. And because we do not know this, we cannot say what happens to the thing that matters most. Not the matter, not the energy, not the information, but the perspective. When the physical system that was running it undergoes the transformation called death. Physics has everything except the thing that matters most to the question. It has matter, energy, information, geometry, time. It has, as we have established across 4 frameworks, no delete function. It does not have you, not as a first-person subject, not as the one to whom these variables are being described. And the absence of you from the equations is not a temporary oversight awaiting correction by better instruments or more powerful theories. It may be, as the hard problem suggests, a fundamental feature of the gap between description and experience, a gap that has existed since the first moment. A physical system became aware of itself and found that awareness nowhere in the physics that described it. That gap is where you live, and it is where the question of what happens to you remains, for now, genuinely and perhaps permanently open. Part 23. The real answer physics gives and refuses to give. Physics gives a clear answer to one version of the question about death. To the question, does the universe delete anything when something dies? Physics answers no. Emphatically, consistently, across every framework, in every language it has, the universe does not delete. It transforms, redistributes, scrambles, preserves in geometry, conserves in quantum states. There is no deletion operator. There is no erasure event. Whatever death is, it is not removal from the universe. But physics refuses to answer the other version of the question. To the question, does my experience continue? Physics is silent, not evasive, not hiding the answer. Genuinely, currently unable to address the question because the question requires a concept, subjective continuity, first-person persistence, that does not appear in the physics vocabulary. This creates a duality that is hard to hold simultaneously. On one side, you have the extraordinary result that the universe never erases you. Every moment of your life is preserved in space-time geometry. Your information is conserved in the quantum state of the universe. The pattern that was you may recur over cosmological time. The physics picture is, in a strange way, maximally conservative. It loses nothing. On the other side, you have the brute fact that the processing stops, the integration ends. The specific organization that made information into experience, that made data into a self, dissolves when the architecture dissolves. And physics cannot tell you whether the end of the processing is the end of everything that mattered. Different philosophical frameworks interpret this duality differently. Hard materialism says that experience just is information processing, and when the processing stops, the experience stops. End of story. The conservation of information is physically real but experientially irrelevant, because the information without the specific processing architecture is not the same as consciousness. Eternalism about time says that the fact of your experience, the events of your consciousness embedded in the space-time manifold, are permanently real regardless of when they occur relative to any observer, a position that does not claim experience continues, but insists it was never less real for being in the past. Some interpretations of quantum mechanics, particularly many worlds interpretations, have their own strange implications for identity and death, implications that physicists argue about vigorously and that we do not have time to fully explore here. The point is that the physics underdetermines the philosophical conclusion. The same physical facts are consistent with multiple interpretations of what they mean for the question you actually care about. And perhaps that is the most honest thing that can be said. Physics describes a universe in which nothing is erased. Physics does not describe a universe in which you are guaranteed to continue. Both of these statements can be true simultaneously. The universe's records are complete. Whether those records constitute a form of existence, a form of persistence, a form of something rather than nothing for the consciousness that produced them, that is a question that current physics cannot answer. And intellectual honesty requires sitting with that, rather than reaching for either the false comfort of physics-based immortality or the false clarity of physics-based annihilation. The honest answer is, we do not know. And the reasons we do not know are deep. Part 24. Einstein's Illusion Revisited. In the beginning of this discussion, we introduced a letter. An old man, one of the greatest scientists who ever lived, writing to the family of his oldest friend weeks before his own death, expressing, with the quiet precision of a physicist rather than the consoling language of a priest, the view that the distinction between past, present, and future is a stubbornly persistent illusion. We have now travelled through 4 acts of physics, 4 frameworks, 4 independent lines of reasoning, and we have arrived back at the same point, but with more pieces in hand. The block universe that Einstein built through the mathematics of special relativity preserves the life of Michel Besso in the geometry of spacetime. Not his consciousness, not his experience, not his subjective perspective. Physics does not reach those, but the events, the moments. Every point on the world line of a man who spent decades thinking about physics with Einstein, who was present at the creation of special relativity in ways that are easy to underestimate from a historical distance, who lived and argued and worked and loved. Those events are coordinates, permanent, embedded. The geometry of the universe contains them the way a sculpture contains the shape of its surface. They are not going anywhere. They were never going anywhere. This is not resurrection. It is not survival in any conventional sense. Einstein was not promising Besso's family that their husband and father was out there somewhere, conscious, waiting. He was doing something more radical and, in a strange way, more honest. He was applying his own theory to grief and saying, the framework we use to describe reality does not support the idea that Besso is gone. It supports the idea that Besso is located differently in the structure. The distinction between present and past that makes us experience his death as loss, that distinction is, in the strict language of relativity, an observer-dependent feature of how we are moving through spacetime. The events themselves do not respect that distinction. They simply are. The stubbornly persistent illusion Einstein referred to is our intuition that the present is real in a way the past is not, that the living are here in a way the dead are not, that existence has an edge you can fall off. That intuition is real as an intuition. It is built into our nervous systems, shaped by evolution, to help us navigate a world where the present is what we can act on and the past is what we must accept. but it is not a feature of the fundamental physics. It is an interpretive layer, a story we tell about a structure that does not have beginnings and endings in the way the story implies. Your life, in the physics picture, is a world line in a manifold, every moment of it permanent, every event conserved, the information distributed but not deleted, the pattern dissolved but the components persisting, the specific organization gone but the possibility of that organization never removed from the universe's configuration space. None of this is what you want when you think about mortality. None of it answers the question of whether experience continues. None of it resolves the hard problem of consciousness or bridges the gap between the physical and the phenomenal. But here is what it does. It tells you that the universe, as best as human understanding can currently describe it, does not treat your life as a temporary intrusion that gets cleaned up afterward. It treats it as an event, a structure, a feature of the geometry. The universe does not have a mechanism for undoing what happened. It does not have a delete function for lives. It can only continue, transforming, redistributing, evolving the states that include the scattered and scrambled information that used to be organized as you. And the question that remains, the one that physics cannot currently answer, the one that is perhaps the deepest question we face as conscious beings aware of our own mortality, is this: is that enough? Is transformation without deletion a form of persistence that matters? Is the permanent embedding of your moments in space-time a form of continuation that means something? Is there something it is like to be the scattered information, the conserved quantum state, the preserved geometric feature? Physics does not know. It has told you everything it can, brought every framework to bear, explored every corner of its own vocabulary for an answer. And at the end of all of it, it stands at the boundary of first-person experience and falls silent. It can describe the outside. It cannot describe the inside. The final act of every conscious being is the act of crossing a boundary that physics can describe from one side only. What is on the other side? Whether there is an inside to the other side, whether there is experience in any form, whether the conservation laws that preserve everything about you in principle also preserve the thing that matters most, remains, at the current frontier of science and philosophy, genuinely unknown. Einstein thought about this. He thought about it with the full force of the intellect that built modern physics. And he wrote a letter, and he died a month later. The manifold contains both of those events. The equations do not mark either of them as endings. The stubbornly persistent illusion of time, of past, present, and future, as real and separate, is the lens through which mortality becomes terrifying. Remove the lens, or at least wobble it, with the physics we have walked through, and death becomes something stranger and harder to categorize, not less real, not less significant, but differently shaped. A coordinate boundary in a structure that does not delete. A transformation in a universe that only knows how to transform. The universe began, or came to be, in whatever sense that means, without you. It will continue, for timescales so vast, the mind cannot hold them, without you. And somewhere, in the four-dimensional geometry of space-time, in the conserved quantum information of the universe's total state, in the configuration space explored by matter and energy over cosmological time, the specific pattern that was you is not gone. It is just no longer the present. And if Einstein was right, and if the physics he built is an accurate description of reality, then present and past and future are distinctions that say more about where you are standing in the manifold than they do about what is real. What is real is the structure, and in the structure, nothing is deleted. That is the terrifying truth about death, according to physics. Not that you are safe, not that you continue in any comfortable sense, but that the universe, at every level of description we have, refuses to perform the operation you most fear it performed. The delete command was never in the code. Where you go, when you go, That is the question physics is not yet equipped to answer. And sitting with that uncertainty, really sitting with it, without filling it prematurely with either comfort or despair, may be the most rigorous thing a mind aware of its own mortality can do.